Hey everybody, in this video we'll be learning about convolutional neural networks, a very interesting type of neural network. Now if you ever used any sort of AI that involves image processing, such as an image classification AI, they likely have used some sort of convolutional neural network. So let's just get straight into it. To first understand how a convolutional neural network works, we'll first need to understand what is convolution. Now to actually see what convolution is, I'll explain it in the context of classifying images. Convolution and convolutional neural networks, of course, can be used for other tasks. However, it'll be easier to understand if we look at it through the context of image classification. So let's take a problem. Let's say we want to classify an image between a square and a triangle. How can we see if the image we have is one of these two shapes? Well, one way we could do that is to look for certain features in our image, specifically certain features that define whether our image is going to be a square or a triangle. So in this example that I'll be using, I'll be looking for the corner of a square, that right-angled corner, or the top of the triangle, as you can see on the screen. And so what convolution actually is we take an image of these features that again define our different image classes, and we overlay it on top of the image that we want to classify. And then we take this image of the feature that's overlaid and we shift it across our main image, across the row, then we move it down, shift it across, and we keep shifting the image until we covered the entire image we want to classify. And as we're doing this, we're going to be looking at the image of our feature and the patch of the image we want to classify that the feature's overlaid on top of, and we're going to see if there's a match between the two images. That will determine whether the feature that we're looking for is present in the image or not. And if it is, that will tell us what class the image is. So now that we cover the concept of convolution, let's take a closer look at what actually is happening. So we said that we had an image of a feature that we overlaid onto the image that we want to classify. Well, what that actually is what we call a filter. And a filter is basically a matrix that we use to identify different features. Now, the values of our filters can correspond to what we want, but for the case of images, we can use the values in our matrix or our filter to represent different pixels. So for our example, since we're dealing with black and white, we could have a value of 1 represent a white pixel, and a value of 0 represent a black pixel. And you'll see oftentimes that filters will resemble the features that they're used to try and identify. So in this example that I have on the right, you can see that our filter resembles an X, and it could be used to identify X's on a black and white image. So how we actually do that? Well, as I said, we will overlap our filter onto the image we want to classify. You can see that the image we want to classify, we could also represent as a matrix of values. Again, for our example, we're using the same system where 0 represents a black pixel and 1 represents a white pixel. And now here's what we actually do. We take our filter as well as the patch of the image that we overlaid it onto. And then we perform an element-wise multiplication between the two matrices. And you can see the result on the right. In this example, we have a filter that looks sort of like a corner, kind of like the corner of the square. And you'll see that the patch that we overlaid it onto is exactly the same. And the result of this element-wise multiplication also looks exactly the same as our filter. What we can do with our result is then take the sum of all the values in this product and For our purposes, if the value is higher, then we could assume that it's a stronger match. So you'll see, again, since we had a perfect match, we had a relatively higher value of 3. In fact, with our example, this is the highest value we could have. Now let's say we overlaid our filter onto a different part of our image. You can see here that the patch of the image that we overlaid it onto doesn't resemble our filter at all. And that is shown in our product when we do this element-wise multiplication. You see, when we take the sum of all the values, we get a value of 0. There's no matching whatsoever. And remember, we said if the number is higher, that means there's a stronger match. So we could assume, since the value is 0, that the feature was not detected. So now that we understand what is actually happening when we do convolution, let's take a look at a visual example. You can see here we have an image of a triangle that we're trying to classify, and we're first overlaying the filter for the corner of the square. You can see on the right the color represents how strong of a match we get. And you can see here that even though we use a filter for a different shape, we could still sometimes get strong matches. Here we have a strong match at the base of the triangle. Right there. However, of course, if we use the filter for the tip of the triangle, you can see we'll get plenty of strong matches as well. Again, we're doing the same process here of the element-wise multiplication between the filter and the patches of our image. Now here we have a square, and of course we'll be using both filters. First, I have the filter of the corner of the square, and you'll see we'll get lots of strong matches. And now the filter of the tip of the triangle. And you'll see here we'll actually get no strong matches. And that indicates that we couldn't find this feature in this image. So here are the results of the comparison of our convolution. And you can see for the image of the triangle, we did get a good amount of matches with our square filter. However, we got more with our triangle filter, and that tells us that our image was in fact an image of a triangle. Now, just keep in mind here, on this image, I do have the word kernel used, and kernel or convolution kernel is just another word to refer to filters. Moving on to the square, you can see that the filter for the corner of the square got way more matches than the filter for the tip of the triangle. So that, of course, tells us that our image is most likely a square. So now let's look some more at convolution and some different elements of convolution. So here I have this representation. You can see that when we do convolution, we're going to have an input. Now, what we were looking at before, we were looking at images, and of course we could use images, but remember that the images, we actually broke them down into matrices, or rather 2D arrays. So what we actually have as our input is a 2D array. In this example, I have a 2D array that's 6 by 6. You can just imagine that every square has its own value. Now, of course, we also have a filter. Here, it's just a 3 by 3 filter. Again, this is what we use to identify our features, and you saw that we shifted it over our image. Now, you can see that our output also is actually a matrix for this filter. In this matrix, every value represents this element-wise multiplication and sum that I talked about earlier between the filter and each different patch of the image. Now, one thing that you'll see in convolution is something called padding. And this is basically where we just add extra empty space around our input image. And we do this for a couple reasons. Firstly, it allows us to identify features that may be in the corners of our image or not fully in the image. And second, you'll see that it also keeps the size of our input and the size of our output the same, excluding the padding, of course. Now, of course, often we also have multiple filters, and you'll see that when we have multiple filters, each filter will have its own output. We could also have multiple inputs, and you'll see this often when we have multiple color channels, for example, like if we're dealing with RGB. And what we do here is we still have one filter, but we just apply it to each input or each channel, and then we take the sum for each output value, and you'll see we get a final output matrix. Here's another example. Here you can see we have 3 inputs, we have 4 filters, and of course, for every filter, it has its own output matrix. Just a couple more parameters you might see. These aren't too important, however, in convolutional neural networks, when you define layers, you also can define these parameters. Here we have stride, and this stride basically controls how much we shift our filter over our input image. So in this example specifically, we had a stride of 2, and that caused our filter to be shifted by 2 each time we overlaid it onto our input. And we could also have dilation. Essentially what this does is this just kind of stretches out our image. You can see that now the area that we're covering is less dense, and our output is also smaller. So now that we understand how convolution actually works, let's take a look at convolution in the context of neural networks. So, as we said, convolution relies heavily on the use of trying to find features, and we do that using filters. However, it's often the case that we don't know what features we want to look for, and therefore we don't know exactly what filters we use. Oftentimes, we'll actually need to look for many different features and therefore have many different filters. If we were to try and come up with appropriate filters for every single case or every single situation that we encounter, that'd be extremely tedious and inefficient. Now, something you may be asking is, if we wanted to do a task like image classification, why don't we use something like a fully connected neural network, which we covered in the Intro to Deep Learning video? Well, the problem with fully connected neural networks on their own is they're simply too inefficient for trying to find filters, and they also don't preserve spatial information. What I mean by that is, well, if you remember, the fully connected neural networks, if we were to give them a matrix as an image, it would actually have to be, a matrix as an input, it would actually have to be flattened down into a one-dimensional array for it to be a proper input. So instead, of course, we're going to implement convolution into our neural networks, and that's how we get convolutional neural networks, or CNNs for short. So now let's take a look at an individual CNN neuron. So if you remember, with convolution, we will have a input matrix, and of course we'll have our filter, which is also matrix, and then we'll have our output. For our input, remember we're looking at it, our image or our input matrix patch by patch. So for a neuron, we'll only use a patch of our matrix as input. And you'll see that every value of our patch is going to be its own value for our input. You could see represented here. Now, if you remember in the previous video, what do we have for each input of our neuron? Well, we have a corresponding weight. So where do our weights come from? Well, in fact, they actually come from our filter. Remember, when we look at our filter and the patch, each value in our patch of our input image is going to have a corresponding value in the filter. So these are what the weights are. And again, for convolution, what do? Well, we do an element-wise multiplication between our patch of our input image and our filter. And then we take the sum of that result. And this is basically, in fact, the same thing that we do when we use a neuron. We take each input, we multiply it with its corresponding weight, and then we take the sum of those products. So that's how the convolution is applied here. It's in fact pretty much the same structure as a neuron. We're just using it in the context of filters and patches of our input image. And of course, that's going to give us an output. And as kind of mentioned before, each individual output in our output matrix, or value in our output matrix, is going to represent our filter being applied to a different patch. So that means rather a different set of inputs. Of course, for like with the neurons we covered before, it still has some of those extra elements. Here we have a bias that we add to our sum, and we also apply a nonlinear function. Often you'll see the ReLU function used. So that was individual neurons. However, of course, we'll have multiple layers, and in these layers, we'll often use multiple filters too. Now, here's an example with multiple layers and how they connect with each other, but there's just one thing I want to point out that we didn't talk about before, and that's pooling. You'll see here that we have these pool layers among our CNN layers, and what these actually do is they essentially just downsize our image. Firstly, how they do that? Well, there's different pooling functions that we could use, but the one you'll most commonly see is this max pool function. What this does is it will look at each 2x2 section of the input image or input matrix, and it will take the greatest value in that 2x2 section, and it will use that as the output. And that's how we get these smaller, downsized input matrices. Now, why we do this? Well, essentially, this is used to extrapolate both low, mid, and high level features. You might have heard this concept before, but let me give you an example. Let's say we have a face. Low level features would be edges of the face. Mid level features might be different features of our face, such as eyes, noses, mouths. And high level features might be something like the entire face itself. So what pooling does, again, since it downsizes our images, it actually causes our filters to be larger relative to the size of our original input image. And that allows us to get different levels of features. Like with the example before, the edges, the mouth, nose, and eyes, and the entire face. So that's why we do this pooling. It allows us to extract different levels of features by making our filters larger relative to the original input image. So there's one more important thing that we actually need in a full convolutional neural network. You see, the CNN layers are extremely good at identifying what are effective filters. However, to actually perform tasks such as classification, we're also going to need some fully connected layers at the end of our neural network. That's what's actually going to interpret the result of applying our filters to the image and then perform the necessary task such as classification. So, of course, when we first create a full convolutional neural network, it's not going to be trained. All the weights, they're going to be initially random, and thus it won't actually be effective at making good predictions. So, how do we train this? Well, it's essentially the same training process that we covered in the Intro to Deep Learning video when we trained our fully connected layers. What we do, we simply first send in our training data through our neural network, and our neural network or our model will make some prediction based off of that, which will likely be quite inaccurate. We'll then see how inaccurate our neural network currently is, compared to the expected values that we want, and we do this using the loss function. Then through the process of backpropagation, we calculate the gradient of each weight, and that essentially tells us how we need to adjust our weights so that our neural network could be more accurate. And then we do just that. We update our weights, and we keep repeating this process until eventually we get a neural network that's accurate. Now, again, in the context of CNNs or CNN layers, our weights are actually our filters. So what we're doing is we're adjusting our filters until they actually are good at identifying features that are relevant to distinguishing between, for example, different classes of images. And then if we wanted to make a prediction, simply we just take our trained model, we send some new data through it, and then it should be able to make an accurate prediction. So now, just to summarize everything that we talked about, we first talked about the concept of convolution and the importance of features in the context of image classification. We saw how filters can be used to identify features in a given input, and we did it by overlaying our filters onto our input and performing that element-wise multiplication and sum. We saw some different ways we could apply convolution and different parameters. For example, padding, we saw that we could have multiple filters, we could have multiple inputs, we could have different stride, different dilation. And then we covered the structure of a convolutional neural network neuron. We saw that we used the patches as our input and we used the filter as our weights. And by the way, this is really what distinguishes CNN layers from the fully connected layers that we covered in the previous video. It's simply how they're connected. Instead of being fully connected, they're connected patch by patch. And then we saw an entire convolutional neural network, how it had the CNN layers, of course. It also had the pooling, which again just downsized our image, and it had the fully connected layers at the end. And that pretty much concludes the video on convolutional neural networks. Thank you all for watching.